Our last problem in Chapter 21 deals with voltaic potential in what we call concentration cells. And so as we set this problem up, I'm kind of going to treat it as we've treated other problems, and then you'll hopefully see how it kind of plays out here. We have a voltaic cell, which we call a concentration cell, and the two half cells are each silver ion half cells. And so what we really have here is we have an oxidation reaction, an anode, that does this chemistry. So this is oxidation. So we're going to have a standard oxidation potential here of minus 0.80 volts. And then in our cathode, we're going to be doing reduction. And that's positive 0.80 volts. Sum up these reactions, and the net of what's happening in this concentration cell is we're going to have silver ions and silver solid. And if we consider what's going on here, we'll see this in a minute, but this is going to be a fairly high concentration because it's a reactant concentration. The silver that we're going to make over here when we start our reaction is fairly low in concentration because we really haven't progressed on in our chemistry. And if we figure out what Ecell is for this, it's negative 0.8 plus positive 0.8, so it's 0.00 volts. So how then is this even going to function as a voltaic cell? Well, what we have to remember here is if we look at the Nernst equation, so Ecell under non-standard conditions is equal to the standard condition Ecell minus, and again, if we're going to consider this happening at 298, we can use our simplified version of the Nernst equation, 0.0592 volts over N times log of Q. The Q for this, because solids won't appear, is basically proportional to the low silver ion concentration, right, that's going to be present in our cathode over the high silver concentration. I'm sorry, this is the anode because we're going to be making it there. Anode over the high silver ion concentration that we're going to have where reduction is occurring, which is going to be our cathode. And remember, as long as these two are not equal to one another, where we're going to have Q equals 1, this is going to be mathematically a significant term. So again, our Ecell is going to be equal to 0 because we essentially have the same oxidation and reduction reaction. So the kind of the force, the spontaneity, comes from the concentration of silver in our cathode being much greater than the concentration of silver in our anode compartment. And hopefully that makes sense. So let's think about this for a second. Think about what's happening in our anode. In our anode, as our reaction proceeds, we're going to be making silver ions. We're going to be filling up our silver kind of half cell. So if we start with a very low concentration of silver to begin with, we're going to be filling that up. And this one is going to increase as the reaction proceeds. In the cathode, we need those silver ions to participate in the reduction process. So having a high concentration of silver provides the reactant that we need here. So as the reaction proceeds, this is going to be used up, and so it's going to decrease as the reaction proceeds. So it decreases as the reaction proceeds. So again, we're going to have this decreasing, this increasing. The reaction stops when the concentrations of silver in the cathode equals the concentration of silver in the anode, right? When silver in the cathode equals silver in the anode, these two are equal, Q is equal to 1, and we no longer have any driving force for that. So let's actually see how much driving force we actually have to start with. because they give us values for our half cells here. So the electrolyte is 0.01 molar in one half cell and 4 times 10 to the minus fourth in another cell. So again, we're going to say we're going to have a low concentration and a high concentration. That's what's going to give us our Q that's less than 1. That gives us our driving force. So our silver concentration that's low is 4 times 10 to the minus fourth. Silver concentration that's high, which is going to be in the cathode, is 0.1. So our Q is equal to 0.04. So in this case, Ecell is equal to 0 minus 0.0592. There's 1 electron that's transferred back and forth in this redox chemistry times the log of 0.04. So we're going to have 0 volts minus, and again, because this number is less than 1, the log of a number less than 1 is negative. So we have a negative here, 0.082758. So we end up with positive 0.083 volts. So one of the things that you'll notice with these concentration cells, they don't have the driving force that we have when we have two different metals, two things that might be far apart from one another on this appendix D, right? You have something that really, really wants to gain electrons, something that really, really wants to lose those electrons. That's a perfect marriage, makes for a strong driving force. Essentially what we're doing with this is we're grabbing something, two things that are the same line on this appendix D, and we're asking in one cell for it to behave in one way as an oxidation, and in the other cell for it to behave in the other way as a reduction. And it's really the concentration difference that is the thermodynamic driving force to provide the spontaneity from this process. And this will continue until their concentrations become equal. This Q value becomes 1, and then because kind of the standard reduction potential, or the standard potential for the cell is 0, once that concentration gradient is gone, there's no more driving force, and the reaction ceases.